So symmetry. This is.
You're still frozen.
You're not recording.
I am recording, but it's frozen up there. So, thank you. So symmetry, and again, this is not on the quiz. So, unit or worksheets 1 through 3 is what's due tomorrow or Thursday, and what's on the quiz. So, sort of a part 2 of this unit starts today, in terms of what's due and what will be tested. All right, so 3 Roman numerals today. 1 and 2 are kind of long. 3 is definitely short. And we're going to kind of jump in assuming you can recognize types of symmetry. So, like, recognize if a graph has what types of symmetry it has. And you know what? To do that, let's do the first couple off the worksheet together. So, change of plans here a little bit. But nobody ever objected to doing homework together, I don't imagine. So look at worksheet 4. We'll do the first 3, I guess, together, and then we'll jump back to notes. Determine whether each relation has symmetry with respect to the y-axis, the x-axis, or the origin. So y-axis just means it's mirrored across the y-axis. X-axis means it's mirrored across the x-axis. What does origin mean, though? That's always the tricky one.
0, 0.
Something about 0, 0. Kind of a diagonal thing. That's not
Where the x and y cross.
completely wrong. It has symmetry with the origin if you can rotate it 180 degrees and it looks the same. Or if you switch x and y and you get the same graph. So let's look at number 1. I think we'll do the first 3 together. So does it have y-axis symmetry? We'll just go overkill with this. So here's the y-axis. If I mirrored that graph across the y-axis, would it copy onto itself? It would not. Right? If I tried to mirror it across the y-axis, then I'd get a piece of the graph up here. So not y-axis. How about the x-axis?
No. It'd be the same thing as the y.
It's kind of the same thing as the y, yeah. If I flipped it across the x-axis, then this piece would go down here. So x-axis is a no. Origin, I don't know how to do a color on this. But here's one way to do it. Hold your paper, don't move your paper. I'm going to move my paper 180 degrees, upside down. Does my upside down graph on here match the graph that you're looking at that's not upside down? Yeah. So that means it has symmetry with the origin. Now that's kind of hard to visualize because you usually only have one graph. You can't rotate yours 180 and then look at your neighbor's while you're, well, Mr. Wolf, I'm trying to find, yeah, I know, but you can't look at your neighbor's paper. So that one's a little bit tricky to recognize. All right. Number 2, does it have symmetry with the y-axis? No. If I flip it over there, it'd be over there. Yeah, there's nothing over there. So y-axis is a no. How about the x-axis? Yes. How about the origin?
No.
Again, I can rotate mine 180 degrees. It's like, wait a minute, it was pointing to the right, now it's pointing to the left, so no on the origin. Now number 3, you're already answering it. Nice symmetric circle. I can mirror it across the y-axis. Yep. I can mirror it across the x-axis. Yes. And if I rotate it 180 degrees, it'll look the same. So all 3. All right, so you've done that before. I think now you're familiar with it. The origin thing is maybe the tricky one. How about number 4, and then we'll jump back to notes. Just the origin. So you don't have to list them all and say yes or no. You could just list which ones they have. Makes it a little easier. So yeah, that one's the origin. All right, let's jump back and let's force some symmetry. So we're going to make a graph have y-axis symmetry. So that means we want to, and I'm going to give us a graph to copy here in a minute. We want to copy across the y-axis. So some people can sort of do this visually. Like if you can visually see, if I mirror it across, then I know what it's going to look like. So some people are more, it's sort of artistically inclined or visually inclined, and they can kind of just make it happen without doing any of the like procedural mathy kind of stuff. For the rest of us mere mortals, here's the kind of process way to do it if you can't visualize what it's going to look like. We'll change the sign of the x coordinates. So if the original graph was +3, then we'll change it to a -3, and that will make it be symmetric with the y-axis. So let's put a real simple picture here that we can copy across. Let's start with a point at -3, -2. I'm going to call that point A. Point B is going to be at 0, -3. And let's make a ray. How about that for a geometry word? From A through B and on forever like that. Now I want to sketch the graph, or maybe complete the graph, to make it have y-axis symmetry. I want everyone to do it the process way with me first, but if you can already visualize what it looks like by flipping it over, hey, good for you. Maybe you've been sort of blessed with that ability to do that. So let's take point A, -3, -2, and I'm going to sort of rename him, or change him, not rename him. I'm going to find A prime, which is the reflected point, and it says change the sign of the x coordinate. So I'm going to take -3, change it to a +3, leave the y coordinate alone, so 1, 2, 3, -2. There's A prime. Okay, well visually I can see, yeah, that A got reflected over there. B is at 0, -3. If I change the sign of the x coordinate of B, it would do nothing. Right? If 0, change its sign, well, it's still 0. And that kind of makes sense because it's on the mirror line or the fold line, so it's not going anywhere. So B and B prime are really the same point. And let's see, this graph went from A through B, so I'm going to go from A prime through B prime. And now I have a picture that is symmetric with the y-axis, meaning I could fold it on the y-axis and it would cross over and match onto itself. So again, if you're adept at just kind of visually moving some points over and then sketching, go for it. If you need to do a little more work and maybe a little more thorough and careful, then that's fine too. All right, let's make a graph have x-axis symmetry. Well, let's follow the same pattern here. We'll copy across the x-axis. That's sort of the visual way to do it. And again, depending on your ability and maybe depending on the difficulty of the problem, that might be enough where you can just kind of visually see and place where to put it. If you want to get some exact points, we'll change the sign of the y-coordinates. So we'll change the sign of the up and down, and so that would flip it over the x-axis. Let's try a picture here. Let's put point. Oh, you know what? Let's do the same graph. So we'll have point A at -3, -2. And point B at 0, -3. And we'll do our ray from A through B. And this time we want to flip it across the x-axis. Now, this one might be even easier since it's not copying onto itself. This point A, if I flip it over, this is almost one where you might flip it on the graph and then write it down rather than writing it down and then putting it on the graph. But we'll go the same order we did. We'll change the sign of the y-coordinate to be a +2. So -3, +2. There's my reflected A. B was at 0, -3. How about instead of sort of mechanically changing the sign of the y-coordinate, how about we just kind of visually see where's this point going to land if I reflect B across the x-axis? Yeah, 0, 3. Which is, of course, what we would get if we change the sign of the y-coordinate. So, I mean, it fits together. You can either change the sign of the y-coordinate, or you can kind of do it visually, and what ends up happening is you change the sign of the y-coordinate. And now we have a picture that is symmetric with the x-axis. Number 3, let's make the graph have symmetry with the origin. This one's for me, it's a lot harder to visualize. Like, I guess I'm usually good enough to see the y-axis symmetry, the x-axis symmetry, but visualizing 180 rotation is kind of tricky to do. For me, again, maybe you can see it, and that's great. We'll talk through how to do it a little more mechanically. So you can rotate 180 degrees, but again, that's kind of hard to mentally picture. I think for me, it's harder to see that. Another way to say it is that you copy it across the x and y axes. since you're copying it across both axes, you'll change the sign of both coordinates. Change sign of both, should have underlined both. Let's again start with that same picture of just that simple line that started at -3, -2. And went through 0, -3. Maybe you can rotate that 180 degrees around the origin, but that is, for me, really hard to visualize where that's going to go. So for this one, I think for most people, it's going to be a little more sort of process-oriented rather than just visualize the thing. So if we change both signs, we get 3, 2. There's the new A. The new B, from 0, -3, becomes, change both signs, 0, 3.
So does that mean our line is now going up?
And yeah, we got to be careful here. The line started at A and went through B. So we want to keep that feature of starting at A and going through B. So something like that. And then, obviously you couldn't do this on the test, but if you're working with a friend, one of you holds your paper steady, the other of you rotates it 180 degrees. It's like, oh, that is the same picture, so I feel pretty good about what it looks like. So sort of forcing things to have symmetry by drawing in the rest of the graph. That's kind of the visual part of the lesson. The algebra part of the lesson, Roman numeral 2, is to determine algebraically if an equation is symmetric. And this is all about showing your work. After we do a few of these, you're going to pick up on a little bit of a shortcut, maybe. I'm not even going to say what it is. After you do some, you'll kind of start to figure it out. But I still need to see the work so that I understand what you're looking at. So even if you can kind of look at it and tell, you need to put it on paper so that I know, what your thought process was. All right, so there's 3 different tests, depending on if we want to check Y-axis symmetry, X-axis symmetry, or origin symmetry. And it's very much related to the graphing part. To graph y-axis symmetry, we change the sign of the x coordinate. We change the sign of x. So the test for y-axis symmetry is to replace x with negative x. We'll do an example of this in a minute if you're like, what does that mean? How does that look? We'll replace x with negative x. Saying the same thing, maybe just a different way, we're going to put negative x in for x. Now you can probably guess what I'm going to write for x-axis. Replace y with negative y. Negative y goes in for y. What do you think the origin test is? Both of them. Place x with negative x, y with negative y. And then after you do that, here's the question for all of them. Is the new equation the same as the original? Is the new equation, after you make this switch, is the new equation the same as the original? And maybe that seems weird. It's like, well, how could it be the same? You replaced x with negative x, so you changed the sign somewhere. And that's going to be the key right there. If it was squared, a squared wipes out the negative, and then you're back to positive. So it's really the squareds and the fourths. Anything with an even power is going to give you some of these symmetries.
Or if it had absolute value.
Absolute value would work as well. Plus you think about the graph of the absolute value.
Yeah.
It has symmetry. So anything that messes with signs is where we can come up with these symmetries. So squaring, any even power, fourthing, sixthing, they'll take care of this stuff. There is a bit of an exception to that, so when we get to origin, we'll have to be real careful. So let's find the symmetry of x equals 2y squared plus 7. So you guys are ahead of the game. There's a squared in there, so I'm already suspicious that something is going to work out because of the squared. Well, let's test them all and see what happens. So y-axis means negative x goes in for x. So in place of x, I'm going to put negative x, and everything else stays the same. And then the question is that the same as the original? No, there's a negative x over there. No, it's not the same. Let's try x-axis. So that means negative y in for y. So x equals 2. But instead of y, I'm going to put negative y in there. And what happens when we square negative y? It becomes positive y, so x equals 2y squared plus 7. Is that the same as the original? Yes. So this thing does have x-axis symmetry. Let's check the origin. There is some links between if it has one or the other or both, but I don't really want to explore those yet. Let's just check it real quick. So negative x in for x, negative y in for y. Yeah, the y gets fixed, but the x is still not fixed, negative. So that's a no. So that thing has symmetry with the x-axis, because it worked when we changed the y, but it didn't work with any other combination. All right, let's try y cubed equals x minus 2x cubed. Any guesses on what kind of symmetry that may or may not have? Just hesitant, which is fine. It's only our second example. So let's go through them and see what happens. So the y-axis test is negative x in for x, Let's see. So y cubed equals negative x. Be careful over here. If I cube negative x, it's still negative, but then that minus sign out front would make it positive. Is that the same as the original equation? No. All right, the x-axis test would be replace y with negative y. And again, you're always looking at the original. Don't. Some people get confused and they start replacing off of the replacement. No, you replace based on the original. So negative y cubed equals x minus 2x cubed. We just said if you cube a negative, it stays negative. So negative y cubed equals x minus 2x cubed. Is that the same as the original? No. Let's try the origin. This feels futile because we're 0 for 2 here. So negative y cubed equals negative x, because I'm replacing both of them, minus 2 negative x cubed. I'm going to be real careful here. I got negatives all over the place. Alright, if I cube negative y, we get negative y cubed equals negative x. We had this problem before earlier, like cube a negative, we get a negative, times negative is positive 2x cubed. Is that the same as the original?
Yes.
Why, yes.
If you divide it by a negative.
If I multiply or divide by negative 1, it is the same as the original. It's like, what magic is going on here? So it turns out that it does have symmetry with the origin. So that's the tricky one. That's why I worked that example. If everything goes negative, you're like, oh, that's way off. You're like, well, be careful. If everything changed signs, well, then you can multiply by negative 1 and make it look like the original, and it turns out it works. So this is the case that you got to be careful with. The squareds part are pretty easy. If it doesn't work, that's pretty easy. But that origin is sometimes tricky because everything changes signs. But if everything changed signs, then it is back to the original. All right, Roman numeral 3, as promised, will be short. It's just more vocab for what we already know. An even function is one that has y-axis symmetry. So it's just another word for y-axis symmetry. An odd function has origin symmetry. And neither doesn't mean it has x-axis symmetry. It just means it's neither even nor odd. So these are words that we use for concepts that we already know. It's sort of like average rate of change is the same thing as slope. Even is the same thing as y-axis symmetry. Odd is the same thing as origin symmetry. So there's not new processes to learn. It's just new words to kind of tie together here. All right, the assignment would be worksheet 4. And it's longer in pages than some of the others, but that's because there's a lot of graphs. So it's 5 pages, but it's still about the same number of problems, and a bunch of them are just yes/no type things. So it's a lot of paper, but I don't think it's a lot of time. And then again, just so no one misses or walks in Thursday and says, "What? Homework is due?" Worksheets 1 through 3 are due on Thursday, or on block day, and we'll have a quiz over worksheets 1 through 3. And again, it's due when we come in and get settled and I say pass them up. If you're not done and you want to use the rest of the time, like while you're taking notes and working on homework to try to get it in, that's fine, but it's going to be late. So like due when I say pass them forward. After that, it's late. So again, you got plenty of time to do it. Worksheet 3 should be completed by now, so it shouldn't be an issue. But just laying that out there. Can I turn it in later today? Can I finish it now? Yes, but it's late. Yes, it is possible to have no symmetry. It's possible that nothing works. If you're looking at number 8, say, yes, that would be no symmetry. Good question.